Good evening to all. Now I am going to explain nomenclature of heterocyclic compounds. So, nomenclature of the heterocyclic compounds. So here, for the fused heterocyclic ring systems, fused heterocyclic ring system is labeled by the letters A, B, C, D, etc. Yes, for the fused heterocyclic ring is labeled by heterocyclic ring is labeled by the letters labeled by the letters labeled by the letters small a, comma b, comma c, comma d, comma e, comma f, etc. So labeled by the letters a, b, c, d, e, f, etc. So here the starting from the atom number give as a one side between one and two. Yes, and the side between 2 and 3 is so on. Okay. For example, we take the here this is a quinoline ring system. In this quinoline ring system, first of all we give the numbering from the this heteroatom. So this is giving us A to next here, B junction, here C. So therefore this is called as a benzo. So this ring is benzo. Here fused junction between these two. Here this ring heterocyclic ring, the homocyclic ring is a B. Benzo B. Here which ring is there? Pyridine. Benzo B. Pyridine. So this is the common name is a quinoline. Quinoline. This common name is a quinoline. Here this is a nomenclature is a benzopyridine. Yes. Next one. here another one is a so this is a heterocyclic ring system and give the numbering from this heteroatom. Heteroatom A, next atom B, next atom C, here then junction. So here this is a homocyclic ring, this is a heterocyclic ring. Here fused position is the first position C and second position D. Only consider the first position but not consider the second position. So therefore this is called as a here benzo, here benzene, here fused position first position C, benzo C pyridine, benzosipyridine, or this is also termed as isoquinoline. So here another one is a so this is a another ring. They give the numbering A, B, C. So this is called as a benzo B thiopane. benzodiazepine. So this is a nomenclature for the heterocyclic compounds. Yes, this type is the nomenclature of the heterocyclic compounds. Okay. So here in heterocyclic ring membering is preferentially given from the heteroatom which is a saturated. So for example, if you give the one of the molecule. So this is a molecule having the substance is there, and another one more molecule. So this is a one more molecule. So now give the nomenclature for these two molecules. So this molecule first of all giving. So in this case, here heterocyclic ring is a ring membering is a preferential. So which is a ring member? Here nitrogen, here nitrogen. Both are the nitrogens is present. So both are the nitrogens is present. So here preferentially given from the heteroatom which is a saturated. Here unsaturation, here saturation. So the numbering is starting from the saturation. So then saturation to the unsaturation. Here 1, 2, 3, 4, 5. 5 numbering. So here 5 numbering. So here 5 atom. So third portion is a ethyl group C2H5 and from fifth portion is a methyl group. So here 3 ethyl, 5 methyl, 1 comma 2 is diazole. 3 ethyl, 5 methyl, 5 methyl, 1 2 diazole. So here in this ring, we are giving the number from 1, 2, 3, 4, 5. So name is a 2 comma 5 dimethyl is here pherol or azole. Yes, pherol or azole. Aza means nitrogen. Zole means 5-member ring. Nitrogen containing 5-member ring is called as a azole. So in the heterocyclic ring with S maximum unsaturated double bond. In heterocyclic ring with the maximum S unsaturated ring is with a double bond. So next one we have studied the here heterocyclic compounds are mainly categorized into two types. That is a pi excessive heterocyclic compounds and pi deficient heterocyclic compounds. So pi excessive heterocyclic compounds means here this mainly based on the relative is electron density on the carbon atoms. The carbon atoms, the heterocyclic ring system with respect to the benzene ring. So here compounds are divided into two types. Then those are the pi excessive heterocyclic compounds, and another one is the pi deficient heterocyclic compounds. So pi excessive heterocyclic compounds means the heterocyclic compounds in which the heteroatom contains its lone pair of electrons. Its lone pair of electrons to the ring is called pi excessive heterocyclic ring system. The enhancement of pi electron over the pi electrons. So in this case, they are called as a pi excessive heterocyclic compound. If pi deficient heterocyclic compound means the system of heterocyclic compound in which the heteroatom withdraws electron density from the ring is known as a pi deficient heterocyclic compound. Simply say as a pi excessive heterocyclic compound means in the heterocyclic ring system, in heterocyclic system, the heteroatom containing lone pair involved in the delocalization of the ring. That is, ring system is called as a pi excessive heterocyclic compound. And in a heterocyclic compound, a heteroatom containing lone pair of electrons that is not involved in the delocalization because the ring containing the sufficient number of the 5 electrons, sufficient number of the 5 electrons. So the lone pair of electron is not involved in delocalization. That type of the heterocyclic compound is called as a 5 efficient heterocyclic compounds. Yes, 5 excessive, 5 excessive heterocyclic compounds, compounds. Next, 5 deficient, 5 deficient heterocyclic compounds. So these are the 5 heterocyclic and 5 deficient heterocyclic compound. In 5 excessive heterocyclic compound means in the heterocyclic compounds, the ring system containing the heteroatom, the heteroatom lone pair of electrons does not involve in the delocalization. So the involvement in the delocalization. Due to involvement of delocalization, the ring system gets high electron density. Ring system gets high electron density. Therefore, this system is said to be pi excessive heterocyclic compound. Okay. So, for example, pi excessive heterocyclic compound. So here the lone pair of electrons is the involvement in the delocalization or a contribution to the ring system because here only 2 pi bonds means 4 pi electrons. So according to Huckel's rule, aromaticity condition, any compound follows three criteria. One is the delocalization of pi electrons and it follows the Huckel's rule. Third one is the all atoms in the sp2 hybridization. So any cyclic compound, it follows the three conditions. The compound is aromatic and it is stable existing. Okay. Otherwise, this is unstable. So that is mainly it follows three criteria. One is the compound mass transfer process a Huckel's rule. Huckel's rule is a 4n plus 2 pi electron system. Says next one, it is follows the all atoms are sp2 hybridization. Third condition is the delocalization of pi electrons. If n electrons is there, delocalization of pi electrons along with the n electrons. N electron means non-bonding electron. Therefore, the system is aromatic. So therefore, here aromatic is stable. Otherwise, it is unstable. Okay. So in this system, here according to Huckel's rule is a 4n plus 2 pi electrons. 2 pi electron system where n is equal to 0, 1, 2, 3, 4, so on. So in this case here n is equal to 0, part of n is equal to 0, the system is containing 2 pi electrons. Or n is equal to 1, the system is a 4 1 ja 4 plus 2 6 pi electrons. Yes, here n is equal to, yes, what happened? 4 to the 8 plus 2, 10 pi electrons. So the system according to Huckel's rule either may be 2 pi electrons, 6 pi electrons, 10 pi electrons. That is the first condition satisfied. So here how many double bonds is there? 2 double bonds. Nothing but the how many electrons? 4 pi electrons. 4 pi electrons. Next, how many here? Here it is not follows this condition either 2 pi electron or 6 pi electron. So how many deficiencies there? 2 electrons. Therefore, a 2 pi lone pair of electrons involvement in here. So one lone pair, a contribution to how many electrons? 2 electrons. So total how much is the 6 pi electrons? So therefore, here condition is satisfied. Next to all atoms are which hybridization is requirement? It is not involvement delocalization, here sp3 hybridization, but involvement delocalization, here sp2 hybridization. So second condition for the aromaticity, all the atoms All the atoms involves sp2 hybridization. So, a lone pair of electron involvement, the nitrogen also sp2 hybridization. Third condition, delocalization of pi bond electrons. If lone pair is there, lone pair of electrons also involvement in the delocalization. So that is a delocalization of the pi electrons and n electrons. So in this case, the pi bonding electron or a lone pair of electrons involvement in the delocalization. Nitrogen containing lone pair of electrons involvement in the delocalization. Therefore, this compound is a pi excessive heterocyclic compound. Yes, heterocyclic compound. Here aromatic or not, that is the secondary criteria. But here compound, here once check the it is aromatic or not. Aromatic or not, it follows mainly three conditions. First condition is it follows Hakel's rule. Second condition is here all atoms are sp2 hybridization. And third one is delocalization of pi bonding electrons. If lone pair of electrons is there, here delocalization of pi electrons with the lone pair of electron. These three conditions is satisfied, the compound is aromatic. So otherwise here what happened? Here lone pair of electrons is involvement in the delocalization. Why? It is also required for the delocalization of electrons, and also it is this lone pair of electrons also required for the aromaticity condition. So in this case, here lone pair of electrons is present inside the ring. Therefore, this ring is a pi excessive aromatic heterocyclic compound. If, for example, in this case, pi deficient aromatic heterocyclic compound. So this is a two possible structure of the pyridine. Pyridine, here one time is a lone pair of electron inside is possible, here another is outside possible. Which is a correct? So here lone pair of electrons inside or outside, that is which is a correct. That can be predicted from the its aromaticity condition. So aromaticity condition, here any system which possesses either apparent to equals to 2 pi electrons or 4 pi electrons or 2 pi electrons, 6 pi electron, 10 pi electron system is a follows the Hakel's condition. Otherwise, it not follows the Hakel's condition. So here, in this case, here we can see the individually. Yes, here 2 pi, 2 pi, 2 pi. So 6 pi plus lone pair, 8 pi electrons. So here what happened? Lone pair is outside. So 2 pi, 2 pi, 2 pi, 6 pi electrons. So ring system requirement how many electron? 2 pi, 6 pi, 10 pi, but not required 8 pi. So therefore this structure is ruled out. So this structure is a correct structure because here inside the inside the cyclic system, here sufficient number of the pi electrons is there. That is 3 pi bond contribution to the 6 pi electrons, and here lone pair of electrons is not required for the aromaticity condition. So that's why here the lone pair of electron not involvement in the delocalization. Only here ring containing pi bonding electrons involvement in the delocalization. The lone pair is not involvement in the delocalization because the ring possesses sufficient number of pi electrons. The ring possesses sufficient number of pi electrons. That's why the lone pair of electrons is not involvement in delocalization. So therefore, this is a pi deficient aromatic heterocyclic compound. Why pi deficient? The lone pair of electrons is not involvement in the ring. So this lone pair is present in the outside. So once outside, it takes electron withdrawal. So here inside the ring, it donating electron density to the ring. So here lone pair of electron is a contribution to the ring system. Yes, electron density contribution to the ring system. But in this case, a lone pair is outside because this lone pair of electron not sufficient, not required for the delocalization. Since already present 3 double bond containing electrons involvement in delocalization. Therefore, this lone pair is outside, and the lone pair is outside. The lone pair is here withdraws electron density on the ring. Therefore, ring is a deficient. Ring is a deficient. Electron cloud is decreases. But in this case, electron cloud is what happens? Increases. This is a pi excessive aromatic heterocyclic compound. This is a pi deficient aromatic heterocyclic compound. Mostly, a 5-member rings are the aromatic pi excessive heterocyclic compound, and 6-membered nitrogen containing heterocyclic compounds are pi deficient aromatic heterocyclic compound. So this is a fight efficient mainly here undergoes electrophilic substitution. Here mainly undergoes the nucleophilic substitution reactions. So once your nature is changes, the reactivity also different. So in this case, nucleophilic substitution reaction takes place. Here electrophilic substitution reactions takes place. This is a fight efficient and high excessive heterocyclic compounds. So now I am going to some aromatic compounds, aromatic heterocyclic compound, which is a high excessive, which is a high deficient. Directly we see. Okay. So these are the heterocyclic compounds. Here furan, thiophene, here benzothiazepine, here quinoline, here isoquinoline, here carbazole, here acridine, here pyrrole, here pyridine. So this is a high excessive, high excessive, high excessive, here high excessive, here high deficient, here high deficient, here high excessive, here high deficient, here high excessive, here high deficient. So pi excessive is what happen involvement of the lone pair of electron inside the ring, and pi deficient is a present lone pair of electrons in the outside the ring. So now in our syllabus, one of the most familiar compound is a indole. So in our syllabus, one of the compound indole. So indole. So this is a indole. Okay. So indole here mainly. So this is also termed as a benzo-B-pyrrole. Benzo-B-pyrrole is termed as a indole. So indole here synthesis indole is mainly present in the indigo as well as some of the drugs is present. So here important it is present in the in medicine. So here mainly five different methods is there for the synthesis of the indole. One is a Fischer-Indole synthesis. Second one is a Maudlin synthesis. Third one is a Nenge synthesis, and fourth one Whistler synthesis, and fifth one is a Resant synthesis. So first of all, we discuss about the Fischer-Indole synthesis. Fischer-Indole synthesis for the indole. Okay. So in facial indole synthesis mainly used for the in this method preparation of the indole derivatives. So in this method phenyl of aldehyde or ketone is treated with the phenyl of aldehyde or ketone is treated with the catalyst like as a S phosphoric acid S3PO4 and zinc chloride or maybe boron trichloride. So in the presence of the here what happen acid catalyst here cyclization is takes place. So then formation of the indole derivative. So first of all in this case, so synthesis here first one Fischer indole synthesis. Fischer indole synthesis. So first one is a Fischer-Indole synthesis. In Fischer-Indole synthesis, mainly you are taking as a S-phenyl hydrogen and S2-phenone is taking as a starting materials. S-phenyl hydrogen, phenyl hydrogen reaction with the S2-phenone. S2-phenone in the presence of acidic catalyst. So acidic catalyst followed by the using the acidic medium and zinc chloride. So here mainly formation of the zinc chloride acidic medium ZnCl2. So then formation of the 2-phenyl indole formation. 2-phenyl indole formation. So this is a 2-phenyl indole. See here, now see this reaction. So medium condensation takes place, then formation of the phenyl hydrogen of estophenone is formation. Phenyl hydrogen of estophenone formation. Once phenyl hydrogen of estophenone, so it is mainly react with the acidic medium. So further what happens? Cyclization takes place. Then this cyclization, further reaction, what happen? Aromatization, then formation of the resulting product. So see this one, phenyl hydrogen, here PH, NH, NH2, phenyl hydrogen, here estophenone, PH, C double bond of CH. So then this formation. See the mechanism, yes, phenyl hydrogen, here phenyl hydrogen reaction with the estophenone. So this is a nucleophilic addition here, the bonding electron shifting. So then what happened? Here this carbon, nitrogen with carbon, here double bond converts to single bond, here lone pair lost positive charge. NH, NH loss of electron positive charge with carbon, here oxygen minus, here pH, CH. Okay, so here the positive charge is unstable. The bond pair electron is taken by this one. It is lost in the form of proton. Yes, this can be taken by the O minus. So once O minus is taken, then NH lone pair of electron. So nitrogen hits lone pair of electron. Here OH, here CH3, here pH. CHPH. So this is unstable because single carbon having the high electronegativity atom on nitrogen and OH. This is unstable. Here spontaneously loss of the water molecule. So then loss of water molecule. Here H and OH. Then formation of the double bond. NH, N, double bond. Here CH3. Here pH. So this is called as a phenyl hydrazone zone of estophenone. Phenyl hydrazone of estophenone. Please take a screenshot. Okay, so now here formation of the hydrogen, vinyl hydrogen of the estophenone formation. Now this is in the here mainly it undergoes the imine is converts to imine is formation. Imine converts to so amine. So that is a tautomerization of the proton state space. Now see here. So here the proton is changes here position to 1, 2, 3 here to here. So that is a tautomerization. That is 1, comma 3 H plus shift, proton shift. Then formation. This is a which is a imine. Imine converts to amine. Here NH, here NH, here C, double bond CH2, here pH. So this is formation. Now here prevention of the here further amine tautomerization by using the acid. So this acid is by adding the acid. This is coming from H3PO4 or H2SO4. So this proton is taken by the low pair of electron. Then what happens? Here protonated hydrogen derivative. here double bond is formation. So now see here, it is mainly involvement in the S 3 comma 3 sigma tropic shift is takes place. So this can be written NH N plus here pH. So here 1, 2, 3. 1, 2, 3. Here upon heating 3 comma 3 sigma tropic shift. 3 comma 3 sigma tropic shift. What happened? The bond electrons attacking here. This is moving and this is migration. So 3 comma 3 sigma tropic shift resulting is a here double bond. Here this is a bonding is takes place in between here third position, here third position, here single bond, here phenyl group, here double bond N H2 plus. Here double bond, here bond is breaking, here double bond NH. So this is a unstable because this ring system is loss of aromaticity. This is a sp3 carbon. So then here what happened? The bonding electron shifting. This is migration. That is a tautomerization. Tautomerization. So then we get the unstable converts to stable. Stable one here NH2 and this is a NH2 plus here phenyl group. So then this is a here electrophilic center is there. This is act as nucleophile here attacking. This is a intramolecular nucleophilic addition. Intramolecular nucleophilic addition. This step is a cyclization. Cyclization. Then how many member ring formation? 1, 2, 3, 4, 5. Resulting 5 member ring formation. Here this can be converted to NH3, NH2, and here which is the phenyl group. So the bonding electrons is shifting, and here loss has a proton, loss of the proton. Then this is formation. pH, here NH2H. So this is unstable, loss of aromaticity. Once aromaticity, so then what happened? This H, this NH2 is lost. So combinedly ammonia lost, then formation of the here aromatic system. So this is a 2-phenyl indole. This is a 2-phenyl indole. So first of all, phenyl hydrogen of S2-phenone is mainly undergoes keto-enol tautomerization, that is a proton shift. Then formation of the S, which is the hydrogen derivative. S, this hydrogen further in the presence of plastic medium, the proton, the lone pair of electrons is taking proton, and here prevention of the S keto-enol tautomerization. Then it involvement in the presence of heating 3 comma 3 sigma tropic shift, then formation of this one, then further tautomerization followed by the new intramolecular nucleophilic addition and loss of the proton, then formation of the our desired product. So this is the Fischer-Indole synthesis. Okay. Next method, Mardulan synthesis. Second method is a Mardulan synthesis. So in this method, here acyl arthotoluidine is treated in the presence of the base, is treated with the acid chloride in the presence of the base. So here first of all in the Mardulan synthesis mainly here acyl arthotoluidine SL-orthotoluidine here reaction with the here SL-orthotoluidine reaction with the base. So then formation of the cyclic compound. First of all, SL-toluidine SL-orthotoluidine here reaction with the base then formation of the indole. Then formation of the indole. So here SL-toluidine. So the SL-toluidine mainly treated with the orthotoluidine. Orthotoluidine. First of all, take the orthotoluidine. O-toluidine. Toluidine. This is treated with the acid chloride. So then, which is formation? Si to orthotoluidine. These are treated with the base. Here, NaNH2 base hydrogen. Then formation of the indole derivative. Indole derivative. So that is an indole derivative. Now see the mechanism of this reaction. So this is a orthotoluidine CH3 here NH2. This are treated with the SiO chloride. SiO chloride. So what happened? This is attacking to here the bonding electron shifting, then donating here loss of the Cl. Here H and Cl loss of the HCl, then formation of the here NH C double bond O R. Here CH2H. These protons are acidic. These are treated with hydrogen, sodalite, NaNH2. This taking proton, the bonding electron shifting. So here loss of the ammonia, generation of the carbanion, CH2 minus. Here NH C double bond O R. This is electrophilic center. Here nucleophilic addition. So therefore here what happens? Intermolecular nucleophilic addition, cyclization takes place, then formation of the cyclic compound. Here O minus, here R. So this is taking proton. From previous cases last proton, then formation of the Here R group, here OH. So this is unstable because here sp3 sp3. Here dehydration takes place upon heating, loss of water molecule, then formation of the desired product. So which is there? 2-vinyl, 2-alkyl indole. 2-alkyl indole is formation. 2-alkyl indole is formation. 2-alkyl indole is formation. So please note this one. Okay, thank you to all.